Okay, hello. Here's the video key for kinetic energy problems. So remember that rotational kinetic energy, or K sub R, is the angular analog to the kinetic energy that we talked about before. From now on, I'll be referring to that as translational kinetic energy. So translational kinetic energy is 1/2 mv squared. Rotational kinetic energy is the rotational analog, so that would be 1/2 I omega squared. So in order to solve for rotational kinetic energy, you need to know both the rotational inertia, I, and the rotational velocity, omega. So here in this first problem, we're given rigid rods of negligible mass. That's convenient, so we don't have to look at the rods having inertia at all. And we're given the distance between the top points and the bottom points, and told that the origin's at the center. Um, and so, yeah, so we're given a angular speed here, so that'll make that part easy. So really, if I'm given omega, all I need is I. So in this case, I have particles, right? So these are point masses. Each point mass is going to have a formula of mr squared for its rotational inertia. So the total is going to be I1 plus I2 plus I3 plus I4. And that would be M1 R1 squared plus M2 R2 squared plus M3 R3 squared plus M4 R4 squared. And if you wanted to make this a little bit easier, you can recognize that these two particles actually have the same mass, the same distance from the rotational origin. So you could just combine those two as 2 mr squared. Um, anyway, so the only other trick to this problem is that the r here is not given by either one of these y values. So we'd have to use Pythagorean theorem to solve for the radius of this little right triangle, or the hypotenuse rather, of this little right triangle that we've drawn here. So that would be 2 meters on the x-axis and 3.05 meters on the y-axis. Solve for r. So once you do that, you can plug it all in, substitute it out, and you're done. So moment of inertia right here. Once you know that, use Kr equals 1/2 I omega squared to solve for part B. And that's pretty much it. So moving forward to the next question here, we have a trebuchet. And trebuchets are awesome physics problems. They also are really kind of awesome middle-aged siege weapons. So yeah, good times. What we're given in this case is a trebuchet where the point of rotation is defined as this fulcrum right here. We have two masses, obviously, and those two masses are different distances away from that rotational point. We're told that it's turning on a frictionless horizontal axle. And we can also say that we can model it as a stiff rod of negligible mass. So the actual rod connecting these two has no mass of any significance, meaning that it has no contribution to rotational inertia. The last thing we're told is that the large mass is just 15 centimeters from the fulcrum. So we know this distance is 0.15 meters. That's my value. You'll have a different value. We also know d, so that means that we can solve for this distance over here as d minus 0.15 meters. So you know the distances of each of these things from the pivot point is ultimately what we come down to. So The question here is to find the maximum speed, and note that it refers to speed, not angular speed or rotational speed. So this is actually asking for v. You can confirm that by looking at the units of the answer, right? V would be given in meters per second. So when it leaves the trebuchet horizontally, you could solve for this using very complicated torque, rotational acceleration, and trigging calculus, but that's doing too much work. Ultimately, the easiest way to solve this is to think about it from an energy perspective, hence why it's included in the energy problem set. So what we have in this system basically is a conservative system, that the energy at the beginning is going to be equal to the energy at the end, total energy, that is. And at the beginning, all of these objects have some gravitational energy. So we'd have the gravitational energy of M1 and the gravitational energy of M2. At the end, after this happens, right, we would say that these objects will have gravitational energy because they're presumably not on the ground, right? That would be a poorly constructed trebuchet. So we'll have UG M1 final plus UG M2 final plus, now they'll be moving. So we'll have some rotational kinetic energy. Now, the question that we need to ask ourselves here is what's going to make this the easiest to solve as far as like where we're defining height 0. So remember that position is always relative. Uh, and so you can define height 0 as whatever you want. My recommendation for this problem to make it as easy as possible is to set the initial height as height 0. This is going to do some weird things on the back end of the problem because M2 is going to be below height 0. It'll have a negative height. And then in our calculations, it'll therefore have a negative gravitational energy, and energy can't be a negative value, right? But as long as you keep in mind that this number is not really a negative energy, it just is more representative of a decrease in energy by a certain amount, then it becomes more reasonable. And the reason I would set the initial height to 0 is if I set the initial height to 0, then this entire first half of the equation becomes 0, right? Which means that my calculations become a little bit simpler. So then over here on the other side, I would have M1 times G times the final height of M1, which in this case is going to be D minus 0.15. That would be the gravitational energy that M1 would have after the trebuchet is vertical. M2 would be M1, or M2, sorry, times G times negative 0.15. And Kr would be what I'm looking to solve for here, right? So given that these are all known values, I know M, I know G, I know this distance, I know M, I know G, I know this distance, you can then solve for Kr. Once I know Kr, I'm going to use that to solve for omega, right? This is a value that I can get my velocity from. So before I can do that, I'll need the rotational inertia of the system. So I'll need to say I equals I1 plus I2. We have two objects here that are both contributing. They're both point masses, so that would be M1 R1 squared plus M2 R2 squared would be my total I. That's not too difficult to substitute in and solve for. Now I know I, and I would say omega equals the square root of 2kr over I. And last step would be to say omega equals V over R, V equals omega times R, solve for V. And that would be my answer. So that's sort of the way that rotational kinetic energy can be worked into a energy conservation problem. Now, the rest of these are conceptual. So while the small mass object is gaining speed, does it move with constant acceleration? The answer here is no. And actually, for all of these next three questions, the answer is no. And the reason is the same for all of them, really. And I actually find it uh, easier to work backwards from the bottom up here. Because if you consider the conceptual nature of this problem, what is causing the system to start to move, right? It's starting to rotate, and that means that there must be a torque. So that torque is RF sine theta. Now, R is constant, right? This is all a solid object, so R is constant, not changing. F is also constant. That would be mg, right? The gravitational force is what's applying the translational force required to cause rotation. And theta is the angle between the two. And theta is not constant. These two values are constant. This is changing. For example, at the very beginning, the angle between the R and FG is 90 degrees. But as soon as this thing starts to rotate, now the angle is greater than 90 degrees, right? And as it rotates more, then the angle becomes even steeper. So theta is changing while R and F are staying constant. If theta is changing, then torque is changing. If torque is changing, then angular acceleration is changing. If angular acceleration is changing, then tangential acceleration is changing, which is to also say that constant acceleration does not exist in this particular problem. Yay! So that's the end of the rotational kinetic energy problems. I'll be posting this video along with a next video of rotational momentum.